All right, guys. So we're starting part two of the chapter 23. So the part two going to be, consists of a couple of sections. One in terms of describing the induced EMF and how it's related to electric fields. The other one is going to be on a circuit element, so a new circuit device that is called inductance. All right, so continuing with the Faraday's law and Lenz's law. So one of the things we understood was that if you have a region where there is a magnetic field, like over here we have into the page magnetic field, and if that magnetic field changes, the conducting loop that is in that, let's say in that region where you have a change in magnetic field, that loop gonna have an induced current. Remember, according to Lenz's law right now, for example, if the magnetic field is increasing, so let's say if the magnetic field that is present there gonna start increase, so this is external magnetic field, right? So this loop gonna try to fight that, right? To try to oppose that change, and it will introduce or pump, out of the page induced magnetic field, to try to fight that increase in the external magnetic field. Now, when it does that, it has to, create counterclockwise current in order to, generate those magnetic fields out of the board, out of the page. And what we would say then, there is a, counterclockwise current. Okay. So if there is a counterclockwise current, right, that means what we can say here is this, right? So in the field change, if the field changes with time, there's going to be counterclockwise current and EMF, all right, induced in that loop, right? So that means EMF going to drive those charges, right? And you're going to have a current counterclockwise, okay? Now, one of the things, if you remember in the chapter 4, when we talked about the, the circuits, we said that in order for you to have a current, you need to have a potential difference, right? Well, remember, the potential difference also related to the electric field that was generated in the current. That means if you have a battery, right? So let's say here's the positive and negative, terminal of the battery. And let's say this is some kind of circuit you had, right? Remember, what you had inside your circuit was the electric field that was driving those charges, right? Pushing those charges in the same direction as the current. We later on say that that's the direction of the current, but remember that is the direction of the electric field, out in your circuit. That means from the positive terminal around your circuit, right, to the negative terminal, there was an electric field, okay? An electric field is, responsible for pushing those positive charges in your circuit. All right, so that means in a way what we have here is, let's say in my loop over here, I can represent that when there's a changing external magnetic field, what I get here is I get, a current in my loop that basically gives me out of the page induced magnetic field. Now, I can also say that that induced current is due to the fact that there has to be, right, electric field in the circuit, in that loop, because electric field is what pushes those charges, and that flow of charges is what we call current. That means that current, which is counterclockwise, is due to the fact there is a, electric field in that loop, right, which then pushes those charges. Then you can have a counterclockwise, current. That means I can even forget about current in this case, right? I can say that when you have a changing magnetic field, external magnetic field is changing, then in the loop you have then the electric field. And that electric field is then pushes those charges, and then you have a current. And then when you have the current, loop then generates out of the page magnetic field, and that out of the page magnetic field will then try to oppose the changing external magnetic field. All right, so that's kind of like, in a way we can then see that magnetic fields are related to electric fields, because as soon as we change those external magnetic field in this region, it generates electric field in the loop, right? All right. And we know that there is a work done, right? The work done by the electric field on the loop in moving a test charge Q once around the loop. Let's say you take one test charge here in the loop, and then as it goes, this electric field basically pushes it, around one time. We know that that's the work done, which is equals to Q times EMF, right? Remember, work done is equals to charge times, potential difference between that, which is, what we call EMF, right? So Q times EMF, which is the work done by this electric field. All right, so work done on the charge by the electric field, then we can say work done equals Q times E times 2 pi R, okay? Because then EMF, right? So the EMF is basically, if you remember, it was a negative of the integral E dot dl, right? E dot dl. And then we can say that this is equals to, since electric field is uniform and constant, we can remove that. And then this dl is going to be the distance as you go from 0 to 2 pi, right? One cycle, sorry, 2 pi r. That means it's E times 2 pi r, which what we get from that integral. Then if I replace this for the EMF over there, then we can see that work done is equals to Q times the EMF, but EMF is written in terms of, electric field times 2 pi r, right? Again, 2 pi r is the distance that the test charge has to cover to go around in one loop, which is basically the circumference, right? All right, so, and that's pretty much, what we get over here. We get that there's a relationship between, a work done and the electric field. Okay, so you can see, right, this Q times EMF becomes Q times E times 2 pi r. Okay, and then we can relate the electric field to the, EMF, which we this is something we have done before, right? Electric field is, remember, we just looked at it a little bit differently. We said electric field was potential difference, right, over distance. Okay, potential difference over distance. Well, it's exactly the same thing, because, well, potential difference here is, our EMF, and then distance here is the circumference, which is 2 pi r. So that's what I can say that electric field is equals to. Okay, electric field is in terms of EMF induced in that loop divided by the, circumference of that loop. All right, so then here's what I have. If I have, let's say, for example, going back, so electric field is equals to EMF over 2 pi r. Remember, this is induced EMF. And remember, according to the Faraday's law, induced EMF is equals to change in flux over time, right? Change in flux over time, or negative of change in flux over time. That means I can come back and replace this EMF, induced EMF, with that quantity, change in flux over time. That means I can see that electric field generated in the loop, okay, depends on the change in flux through the loop. And that's what we have, right? There is a change in flux because the magnetic field external is changing, so the magnetic flux is changing. Yeah. So remember, magnetic flux, since it's equals to B times A, and there's also a cosine, but we can see that the magnetic field, is perpendicular to the plane, so that cosine of theta is 1. So we can say that flux is B times A. And if the flux is changing over time, is due to the fact that magnetic field is changing over time. That means what we have here is, since it's a circular, area, A is equals to pi r square. So then we can say, change in flux, which is B times area, or B times pi r square, but pi r square doesn't change, so we can remove that. And what we get here is just dV dt, okay? And from that, we can then say that electric field, right? So electric field is equals to negative of, this is the radius of that loop over 2. So those are things that don't change. But then you have here change in magnetic field over time, okay? And this means that you have something that relates electric field directly to the magnetic field. It says that you generate electric field from the magnetic field, but there has to be a changing magnetic field for you to have an electric field, okay? So that means that this is kind of like, you can see a modified version of the Faraday's law. Okay, so which is known as the Faraday's law of induction. It tells you that change in flux over time, remember, it was equals to EMF induced, but now we know that EMF induced, remember, from that equation is also E dot ds, closed integral of E dot ds. And this equation basically gives you the relationship between magnetic field and electric fields. That means what you get here is you can generate electric field using the magnetic fields. But what you have to do in order to get electric field is to change your magnetic field as a function of time. So if you change your magnetic field as a function of time, then you can have an electric field. If your magnetic field is not changing as a function of time, that means it's constant, then you don't get electric field. That means you kind of get, in terms of like, let's say, the condition, I guess you can say that the condition to generate electric field, you need change in magnetic field or change in external magnetic field through the loop. All right, so the induced electric field is a non-conservative field that is generated by a changing magnetic field. Okay, and what we get here is this type of electric field is very different from electrostatic field, because electrostatic field, or the electric field generated by the stationary charge, was conservative. That electric field could conserve energy. This electric field does not conserve energy, so that's why it's a non-conservative electric field. So you have completely two different electric fields because two different source, right? Electric field generated by the point charge is conservative because it basically can convert your energy, potential energy, into the kinetic energy. But if you're talking about then let's say electric field generated by the change in magnetic field, this one is non-conservative. Okay, remember, because one of the things we have here is that when there is a magnetic field, and magnetic field gives you, let's say, magnetic forces, right? Remember, magnetic forces do not change your kinetic energy, right? They don't change your kinetic energy. So that means delta K is basically zero. And if there is a then potential energy, then potential energy cannot be converted to the kinetic energy, okay, because your kinetic energy does not change. All right, so that means you have two types of electric fields, one generated by a point charge, another one generated by the changing magnetic field. Okay, so the next we're going to talk about inductance. And inductance, as we're going to see, right, generally going to be it can be in a let's say DC circuit. It can also be in an AC circuit. We don't necessarily go over AC circuits in this class, so we're just going to talk about inductance as a circuit element, right, as a device that is in a DC circuit. Remember, DC circuit compared to AC circuit, the difference that in a DC circuit, let's say here, if I have a potential, right, or EMF, that EMF does not change as a function of time. So that's kind of like the difference between DC and AC, where if I have an AC circuit, potential or the EMF changes as a function of time. Every second, right, it's either decreasing or increasing, and we have a, let's say, fluctuating a potential and current. All right, so what we have here is an isolated circuit, and think like this. So you have the EMF source, and this is EMF from the battery. Okay, this is EMF of the battery. Okay, and then what you have some kind of resistive load in your circuit and a switch. Okay, so you have kind of like, I guess, in a way, switch is not a really circuit element, or all it does is just basically makes your circuit open and close, right? And whenever you have a closed, switch, it makes a closed circuit, so then the current can run through your, let's say, through your circuit. Okay. Now, one of the things we have here is this, and this is not something we considered before, but we can start considering now because we just learn about that current running through the through the wire, right? Current running through the conducting wire, generates its own magnetic field. Okay, and that's one of the things we can see that effect of that magnetic field generated by the conducting wire. Okay, we can see, right, when the switch is closed, the current is in the running in the circuit, but current does not go to its maximum value instantaneously. Okay, it doesn't just go from 0 to, let's say, 2 amps instantaneously. Okay, because one of the things we have here is, according to Faraday's law, right? So we learned that as soon as you have a let's say, current in a wire, it then generates magnetic field. Okay, so, and we know that magnetic field generated by the conducting wire is proportional to the current. Okay, so now what we get here is this. So let's say this is the area of my circuit, right? So that's the area. And as soon as my current, right, you can see, right, as soon as my current in a circuit starts increasing, so let's say starts increasing, that means magnetic field through that, area of the circuit starts increasing. And this is basically an external magnetic field, okay? But what we get here is this. If that magnetic field starts increasing, that means the flux, right, through that loop starts increasing, okay? Because, now you can see, right, out of the page magnetic field everywhere inside this, let's say inside your loop, right? You can think like you have a rectangular loop, right? And everywhere magnetic field here is out of the page. Okay, that means that magnetic field out of the page will start increasing because current in your circuit starts increasing, and magnetic field is proportional to the current. Current starts increasing, magnetic field starts increasing, the flux starts increasing. Okay. Well, then if the flux start increasing in your let's say circuit, then we learn, right, if you have a change in flux through that area of the loop, well, what it does here, it induces EMF in your loop, right? Induces EMF in your loop, okay? And this induced EMF has nothing to do with the EMF of the battery. So this is then basically your loop itself trying to then oppose that change, okay? And this direction of this induced EMF is such that it would, cause an induced current in the loop. That means this guy causes induced current in the loop. And it's always going to be in a sort of like an opposite direction, right? So in opposite direction, because one of the things we're going to have here is it's going to try to oppose this increase in magnetic field, okay? That means it's going to try to generate its own magnetic field, which is, let's say, into the page. So let's try to have a different color for that. All right, so let's say this is going to be then induced magnetic field, which is going to be then into the page. And then we can see, right, for that, there has to be induced current, which is going to be clockwise. So this guy here is counterclockwise. This guy has to be then clockwise, okay? So this is the battery current, and this one then is going to be induced current. Okay, that means the current itself induces, circuit itself induces current to try to oppose that change. Okay, that means it tries to generate its own magnetic field to oppose the change in the original magnetic field. Okay, basically exactly what the Faraday's law describes. Okay, and obviously, let's say EMF over there is going to be then, this is negative, this is positive, right? So that, let's say it establishes sort of like an EMF here, somewhere like that, where then the current is running, clockwise. All right, so this is sometimes known as a back EMF. Okay, so we can say that this is back EMF. Okay, because what you have here, you have a EMF that is generated that try to go in the opposite direction. Okay, so it's going to oppose the direction of the EMF in the battery. It's always have the opposite polarity. Okay, and one of the things we have here is, because of this induced current in the circuit, this original current doesn't increase to its maximum value quickly. It kind of gradually increases. Okay, that means this induced current is fighting and fighting. Well, eventually, let's say the maximum current is reached, but it doesn't go and reach maximum if it didn't have that induced current. Basically, it's not as quickly if it didn't have. So it takes a little bit more time to actually reach the maximum value. Okay, and this is due to the fact that circuit itself basically opposes that increase in current. So that's why you can never find a circuit where the current reaches the maximum, value, instantaneously as soon as you close the switch. There's no such thing, because it doesn't matter how, you know, let's say ideal your conductors are. Remember, there's no such thing technically as ideal conductors. All the real conducting wires, right, do have this back EMF. Okay. Now, whenever then you have a circuit like this, where you have the circuit, opposing the increasing current in the circuit, from the battery, then you can say that the EMF, we're gonna call this self-induced EMF. It's sometimes called back EMF, but the more proper name is self-induced EMF. Okay, which is this guy over here, right? So this is self-induced EMF. Okay, that means your circuit induces EMF opposite to the EMF of the battery to try to fight that increase in magnetic flux through the loop. Okay. Now we can even calculate this. Because again, we know that this is due to the fact that there's a change in magnetic flux. Okay, because there's a change in magnetic flux. So then we can calculate this, and we can call this, we're going to call this L, because the inductance, right? That means when the circuit induces EMF, one of the things we can say that, there is an inductance in the circuit. And generally inductance is given with this capital L. In a way, you can say that induced EMF is proportional to negative of change in flux over time. And if there's an n number of turn, right, then you can also, let's say, have that. And remember, so technically that n is part of the, let's say, induced EMF equation, right? Because you can have a, multiple turn in your loop. So you have this equation, right? And then one thing we can say here is, this is due to the fact that there's a change in current in the circuit. So then you can say that induced EMF is proportional to the change in current, right, in the circuit. And then when you go to proportionality sign to equal sign, you introduce a constant, and that constant is here L, which is inductance of that coil. Okay, so L times then dIdt. Remember, you need to have a change in current, right, in order to have induced EMF or self-induced EMF. Okay. Now the L here is, you can see, right, it's called the inductance of the coil. Okay, inductance of the coil. And generally what we have here is the inductance, right, is sort of like, let's say, an effect where the circuit itself is opposing change in, let's say, the current in your circuit. Okay, but because you can see, right, so since this induced EMF depends on changing current over time, then you can say that as soon as your current becomes maximum and steady, and that means the IDT is 0, right? There is no change, then induced EMF goes to 0. Okay, that means that's why once you have a steady current, then you can completely ignore this inductance or this, let's say, self-induced EMF and self-induced current in the circuit, because it usually only present maybe like, let's say, for a second or 2 seconds, only during the time when the current is increasing from 0 to its maximum. Okay, but as soon as your current, let's say, reaches its maximum value, there is no more induced EMF, there is no more induced current in the circuit, and then you have like just a general, let's say, DC circuit with a battery and a single resistor. Okay, now, but most of the time, let's say during that portion where the current is increasing or decreasing, you do have a back EMF, you do have a self-induced EMF, and you do have to take that into account and use that in your equation. Okay, and one of the things we see here is that we're going to see some of the equations. So this induced EMF, right, only depends, or this, sort of like this inductance, right, L, which is the inductance, only depends on the geometry of the coil or other physical characteristics. It's very similar to the capacitance C of the capacitor. Remember, the capacitor was epsilon naught times area over the distance, and there was also a kappa, right, dielectric constant. But you can see, right, it's area and the distance. So technically the only thing capacitance depends on the physical properties of the capacitor. Same way we're gonna see that inductance, right? Which is the inductance is the value that we can calculate for that device, right? Is basically also just depends on the geometry of that, let's say coil, okay? Because sometimes your conductor, right, can be like, in loops, right? And then actually can increase the, let's say this effect by many, many times, so. All right, so now the best, let's say, for example, right, the best way to look at this, inductance is to understand that, again, this is due to the fact that there is a change in flux, right? There's a flux that is changing in your circuit, so that's why you have this inductance, okay? Then you can say that if you have n number of turns, and this is then the magnetic flux, so then you can take the number of turns times the magnetic flux and divide by the current. Okay, so then this gives you the inductance. That means it's a ratio of the magnetic flux divided by the current. Okay, and you can see, right, L here, N here is kind of like just a constant, right? I mean, just a number of turns. Okay, that means you have several equations for the inductance. Okay, inductance, you can say that here's equation 1 in terms of then, let's say flux and the current, right? And then you have also this can be written in terms of negative EMF induced, by that inductor, and then divided by, di dt. Di dt is basically the change in current, right, in your circuit as a function of time. Okay, that's why as soon as there's changing current, right, there's no change in current, there is no sort of like inductance. And you can see, right, the inductance is a measure of the opposition to a changing current. Okay, opposition to the changing current. Okay, and compared to resistance, which is opposition to the current. So that means, remember, so resistance here is directly, let's say related to the current, right? It's opposition. It's inverse of the, current. So like, let's say, remember, resistance is equal to V over I, right? So that means, it depends on directly, or so inversely, but it's, opposition to the current, where the inductance is opposition to the changing current. So inductance is proportional to 1 over then di dt, okay, changing current. So the units for the inductance is Henry, after Joseph Henry, who did a lot of contribution to understanding, this magnetic effect, right? So basically concept of induction. So 1 Henry is equals to 1 volt times, seconds per amps, which is, using this particular equation, you can see, right, it's volts per amps per second, because EMF is volts, di dt is amps per second, and if you move the second up, becomes volts times second over amps. Okay. All right, let's look at then an example here where we can try to understand how the solenoid, which we talked about in previous chapter, right, can be used to induce EMF, in your circuit. Okay, so solenoid, you can think of like, let's say if you put a solenoid in your circuit, then you can actually have, this induced EMF. Okay, all right, so let's look at it. So consider a uniformly wound solenoid having n turns and length L. Assume L is much longer than the radius of the windings and the core of the solenoid is air. Okay. Find the inductance of the solenoid. Okay. Now, to find the inductance of the solenoid, we know that through the, thing like this, remember? So this is kind of like the solenoids, right? So number of turns like this, so many turns. So where there's a radius R, right? And there's a length L, or, actually use this L over there. So there's a magnetic flux because it's going to generate, some kind of magnetic field through the solenoid like this, for example. Okay. The magnetic flux is equals to B times A. Okay. Now, we know that, remember the Ampere's law, that last example from the chapter 22, we found that using Ampere's law, the magnetic field through the solenoid is mu naught N times I. Okay. So this was the magnetic field, to the center of the solenoid. Then this is magnetic field times area, okay? And you can see from here, is, remember, this N was a concentration, number of turns per length. So we can replace that. So we get mu naught times N, which is number of turns per length, times current, times area. Okay, that's the magnetic flux. Okay, and this, inductance is equals to N times the flux over current. Okay, that means this flux here is that whole thing. Okay, that means, what you get is N times that, so it becomes N square. So then mu naught times N square, and there's a current here which cancels with that current over there, N times A. And you can see, right, this is the inductance of the solenoid, which means it only depends on number of turns in the solenoid square, area of the solenoid, and then the length of the solenoid. Okay, that's it. So N, number of turns, length, and then area, which is going to be usually pi r square. And those are the values that represent the geometry of the solenoid itself. It doesn't depend on how much current running through that. It doesn't depend on anything else, just on the geometry of the solenoid itself. So that's why you can increase the inductance by, having more turns. You can increase the inductance by having bigger area, or you can decrease the inductance by, increasing the length of the solenoid. And those are the things that, and this is nothing but, proportionality, magnetic constant. All right, so let's look at part B. So calculate then the inductance of the solenoid if it has 300 turns, length of 25 centimeter, and its cross-sectional area is 4 centimeter squared. That means, this equation that we just derived, we can then try to use it to calculate the inductance. Remember, so that means we have this L, which is the, equation that we just derived, right, for the inductor. So L is equals to N times, N squared times mu naught times the area and divided by the length. Okay, so if I use this equation, so what I will get here is 300 turns. Mu naught, remember, was 4 pi times 10 to the negative 7. Then area is 4 centimeters square, which will end up being 4 times 10 to the negative 4 meters square. And this is divided by the length, which is 25 centimeters, so it becomes 0.25 meters. Okay, so if I then calculate this, we can get 1.81 times 10 to the negative 4 Tesla times meter square over amps. So that's, the unit for the, inductance. Okay, so Tesla times meter square over amps. All right, so we can just write it down as also 0.181, millihenry, because those quantities together is basically Henry. Generally, the value for the inductance are, between, let's say, maybe let's say micro Henry to maybe like a Henry or something like that. So you're never really going to get a really large value for the inductance. That means very rarely you're going to get larger than, let's say, 1. And, very rarely you're going to get value, smaller than, let's say, micro. So maybe let's say nano Henry or something like this, is a very small inductance. And that's why it can be neglected. And something like 1 or 2 or 10 or 100, especially like 10 and 100, you're almost never going to see inductance like that, not in problems like this, at least. All right. So let's look at one more example here. It says calculate the self-induced EMF in the solenoid if the current it carries decreases at the rate of 50 amps per second. All right. That means what we get here is, current increase or decrease is what responsible for the, induced, EMF, right? Induced EMF and, inductance, actually being, let's say, some kind of, let's say, not a factor, right? So now becomes a factor actually into considering, like, let's say, what's going on in the circuit. as long as, or you can say you have a, you know, changing current, you then have contribution from this inductor as a device. And we can calculate that, you know, self-induced EMF, and that equation was negative L times di dt. Now that we calculated the inductance value, right, L, then we can, you know, plug in that inductance value, which was 1.81 times 10 to the negative 4 Henry, and then changing current. And we're told that changing current here is 50 amps per second. Okay. And what we're going to do here is, since the currents, say di dt, since it is changing, so we are told that it is 50 amps per second, but because it is changing, it's negative 50 amps per second. So you put the negative over there, and those two cancel each other, and you get 9.05 times 10 to the negative 3 volts, or 9.05 millivolts. Okay, and this is the value for the induced EMF. That means the solenoid generates potential difference between 10, and those are the values for that. Okay, and you can then see from here that it's a reasonable amount of, you know, potential difference. So it cannot be, let's say, ignored if you're considering, let's say, a system where there is a solenoid, which gives you a reasonably large value of the inductance. All right, so one more example here. So we have an inductor in the form of a solenoid, again, contains 420 turns and is 16 centimeter in length. A uniform rate of decrease of current through the inductor of 0.421 amps per second induces an EMF of 175 volts. Okay, what is the radius of the solenoid? All right, so one correction that I'm gonna make over here is that it's actually 175 microvolts. So 175 microvolt, okay. Because 175 volt is insane amount of voltage for, you know, an inductor as a device. It's almost impossible. All right, so, but 175 micro is like, you know, 0.175 millivolts, which is, you know, reasonable, as I say, right, for the inductance value. Okay, that means we're given the number of turns, right? So 420 is number of turns, 16 centimeter is the length, 0.421 is the di dt, right? You know, rate at which the current is changing, and we're also given the EMF, okay, induced EMF. We want to find this radius of the solenoid. So what should be the radius of the solenoid, so that we get all those, you know, or you get this induced EMF for those particular geometry of that solenoid. All right, so we can see that we have several terms, right? So we are given induced EMF, we're given, you know, di dt, which is change in current, we're given number of turns, we're given the length, okay? And one of the things we can see here is we need to kind of figure out how to, you know, use these quantities to find then the radius r. Remember, the radius r is technically in this, you know, in the part where you have the area, right? So area is, you know, let's say the quantity where there is the radius, because, you know, area is always pi r square for the solenoid. Okay, so you can see, right, the radius is exactly what we're trying to find. Now, we're not given anything about, you know, the inductance. You're not told what is the inductance value. But one thing we get here is that we know that, for example, EMF is equals to L times, you know, di dt, right? So let's say, remember, you can kind of use absolute value for those things. So EMF equals, this EMF, right, is L times di dt. All right. So that means, you know, L is equals to, right, if you kind of look at it like this, EMF over di dt. Okay. Well, we also learned if this is the inductance of a solenoid, okay, it is also equals to n squared times mu naught times the area over then the length. That means this is, you know, as a term, right, in EMF over the, you know, di dt, is equals to, n squared mu naught times A over L. That means what we're doing, we're just substituting, right? All right, so I can rewrite this in terms of, so mu naught n square, and A becomes like, let's say, pi r square over L. And then you can see right from here, I pretty much have all the quantities, see I have the EMF, I have the dt, I have number of turns, I have the length. The only thing I don't have is the radius. So I rearrange this and just solve for the, for the radius, right? So you can see, right? So I have then radius square, move everything to the other side. So it becomes EMF of the inductors times length. And this is divided by mu naught times n square times pi, then times di dt. Okay. And then, take the square root of both sides. All right. So then here what I had is EMF 175 times 10 to the negative 6 volts, the length 0.16 meters, divided by mu naught 4 pi times 10 to the negative 7, then times number of turns 420 squared, then times pi, then times the IDT, which is 4.421 amps per second, right? So take that, plug it into the calculation, and what we get here is 9.77 times 10 to the negative 3 meters, which means it has to be 9.77 millimeter, let's say having a radius of 9.77 millimeter for the solenoid. Only then the potential difference, right, will be 175 microvolts. Okay, so that's why you can see, right, in a way, anything bigger or smaller will induce a different amount of EMF. Okay, it will still be an EMF, but just a different amount of EMF. All right. Now, we've been talking about this inductor, right, as a device. And a lot of times we can actually have that inductor as a circuit element in the circuit. So let's say I can take this solenoid and place it in a circuit, and this is the symbol then I'm going to be using for the solenoid. So whenever there's a solenoid, and here's the thing, there are other geometry that I can use for the inductance, but just like there are other, let's say geometry I can use for capacitors, most of the times we use parallel plate for the capacitors. Same thing is here. There are other, shapes I can, use for the inductor, but the most commonly used is a solenoid, okay? Because that's why we derive the, equation for the inductance for the solenoid. Remember, if your inductor is solenoid, L is equals to n squared times mu naught times area over the length, right? So this is basically specifically for the solenoid. You can have other, shapes, right? And you have to calculate or derive the equation for the solenoid for that, right? You can have a toroid and this and that. So, but in this class, we're mostly going to be concentrating on, let's say, solenoid to be the inductor. All right. So, and here's, what you're going to have. So let's say if you have connecting to the, let's say the battery, and maybe could be another resistor, right? So you can have this. So L is the inductor, R is the, resistor, and this is generally LR or RL circuits. So this is not as LR or RL circuits. That means you have a resistor and an inductor. Sometimes you might even have a capacitor there as well. Okay, so this is known that RLC circuits. That means capacitor, inductor, and a resistor in the circuit. Okay, so you can have LC circuits and things like that. Okay, so that means you can have a number of those, configurations. All right, so what we do here is we assume that the self-inductance of the rest of the circuit is negligible compared to the inductor. That means, even though, for example, I have this a battery, let's say, connected to the inductor, so technically all those wires can provide a little bit of inductance, right? This, self-induced EMF and, let's say a current. It's so negligible we can ignore it. We can say that this guy here, right, is dominating everything else in terms of providing the induced EMF and induced current. So that's why we can say that if some portion of your circuit has a large self-inductance, which we're going to now start calling inductance instead of self-inductance, just inductance, right? So I can have that as basically represented with that symbol. Okay. All right, so you can see, right, even without the coil, circuit will have some self-inductance, okay? Do we need to calculate, when it's very low? Probably not, because it's gonna have a very, very, little effect, but generally that's kind of like the idea. All right, so then let's look at some RL circuits, okay? So what we have here is a resistor inductor, configuration. They're in series. So you can see right here we have an external battery EMF source, and what we get here is we get switch 1, switch 2. So you can see, right, switch 1 basically connects battery to, let's say, switch 2 and resistor and inductor. But then you have a switch 2 which can go to point A to point B. So let's say when the switch 2 here is thrown at point A, that means if I close switch 1, there's going to be current running like this in the circuit. Okay, and that's kind of what we're going to start with in our circuit. That means we are looking at let's say a circuit where, for example, there will be a current only after I throw the S2 to point A and S1 close it. Okay, that means you can say that when the when that switch is closed, which is going to be exactly at t equals 0. Okay, so let's take t equals 0 the instant when we close the switch. Okay, the current, remember, was 0, even like a fraction of a second before that. So the current in the circuit, right? So this current over here doesn't just automatically go to its maximum value like instantaneously. Okay, it doesn't happen instantaneously. What happens here is it begins to increase. Okay, it begins to increase. Okay, now as it starts increasing, the circuit, right? Well, this guy here is an inductor. That means it has ability to oppose that increase in a current from the battery, right? So then the back EMF is induced in the inductor that opposes the original increase in current. Okay, so it's going to try to fight it. Okay, it's going to try to fight it. Then in a way, what I get here in the circuit is, so for example, right, you can see, right, so let's say kind of like, let me do those. There's a current like this, right? There's a current like that, right? And I have the 1, 2, and 3 circuit elements. So according to Kirchhoff rules, EMF minus remember this is the loop rule. So minus current times resistance, then minus potential difference or EMF, across the inductor, and that's going to be in terms of EMF L, right? And then this is equals to 0. Okay, that means this is the instant where you have t equals 0. So let's say this is the general equation for your loop. Okay, that means EMF, you can see, right, as it goes from here, again EMF, and then lose at the here at the through the resistor, then through the inductor, and come back, and that's a 0. Okay, all right, so what we get here is this then. This is generally, like, say, if I replace this, I have EMF minus then the current times the resistor minus this is EMF across the inductor. And remember, this is equals to inductance value times then the IDT. Okay, this is 0. That's why, remember, the resistor is directly proportional to the current, where the inductor is proportional to the changing current, in time. That means, it, or we can say it depends on changing current in time. All right, so if I try to then find, let's say, what's going on in terms of the solution for this equation, it's very difficult, right? So this is actually a differential equation, so it's much more complicated than, let's say, using the equation for the RC circuits and things like that. Okay, so the idea here is that as soon as you close the switch S1, assuming that S2 is already at point A, right? As soon as you close the switch S1, the current that is generated starts increasing by the battery, right? But the inductor right away tries to fight it. Okay, it tries to fight it, and it tries to then right away decrease the current to 0. Because remember, there was thing like this, there was no current in the circuit. Now you start increasing the current. That means, the inductor tries to oppose that. So it's going to try to, generate its own current in the opposite direction. So let's say this is going to be then induced current. Okay, this is going to be then induced EMF, and it's going to try to fight it. Okay, and you can think of like, let's say at t equals 0, then what you end up here is this guy is basically almost 0, because there, that current coming from the battery is canceled by the current generated by the inductor. That means this I induced is equals to I at least at that instant. Okay, and after that, remember the battery still pumps more, let's say electric fields and things like that. So gradually this current as a function of time, right? So it gradually starts increasing, and it starts increasing. Then the potential difference across this inductance starts decreasing, and the potential difference across the resistor starts increasing. Okay, and what happens here is at t equals 0, all the potential was across the inductor, and then at a later time, all the you can see all the potential across inductor starts decreasing, because as you can see, right, as the current becomes more steady and more constant, the IDT as a function of time starts decreasing and decreasing exponentially like that. That means as the IDT decreases, this guy over here starts decreasing. EMF of the inductor slowly starts decreasing, and the EMF for the resistor slowly starts increasing. So what happens when the current is constant? Then the IDT goes to 0. Well, if the IDT goes to 0, EMF across the inductor goes to 0. That means all the EMF provided by the battery is basically across the resistor, and resistor just dissipates energy, doesn't fight the current, right? They just dissipate, let's say energy, and dissipates the potential, let's say. And one thing we can do here is we can understand that. All right, so now let's say you start with this equation. Let's say what we want to know here is what is then the current as a function of time, right? So the current as a function of time as it starts increasing and reaches its maximum. Okay, and can we have something like this? So it's increasing like this and then saturates and reaches its maximum. Okay, so that's why the inductor affects the current exponentially, and then the current does not instantly increase to its final equilibrium value. And if there is no inductor, the exponential term goes to 0. So you can see, right? So what you get here is, this is EMF over R. So this is like, let's say your maximum current. Then you have 1 minus e to the negative t over tau. This is exactly what we did for the charging of the capacitor, in a way that very similar equation. But the tau here has nothing to do with the a capacitor. It's still a time constant, but this is in terms of inductor and a resistor in the circuit, right? You can see, right, if there is no inductor, the exponential term goes to 0, and the current would instantaneously reach its maximum value as expected. But because of the inductor, that takes a little bit of time for the current to reach its maximum. And then we have this time constant value, which is tau, Greek tau, equals inductance value divided by the resistance value, and that gives you the time in seconds. Okay, and what it does here is whenever you calculate over here, right? So let's say you get 0.5 seconds. That gives you the time required for the current to reach 63.2% of its maximum value. That means in half a second, right, it reaches its 62% of its value, maximum value, and then a little more, right, then it reaches maximum. That means this time constant gives you how long it will take for this, for your system, right, your current reach roughly 63% of its maximum value. That's what sort of like a time constant represents. All right, again, you can see, right, here's that graph for the current as a function of time. So you can see, right, as it increases, so that this is as a function of time, you can see, right, this is the tau, how long it takes for it to reach this 0.632 times EMF over R. Again, EMF over R is what we call maximum current, right? So you can say that, tau is the time for it to reach 0.632 of that EMF over R value. Okay, so the current initially increases very rapidly. You can see, right? So when you close the switch, EMF, drives the current And even though like the inductor tried to fight it, you still have the current, right? The battery current, changing its value. You can see, right, um, rapidly here, right? This portion here is a very quick change. But then as soon as it gets, let's say 70 or 80% of its value, it's kind of saturated and it takes a very long time to reach its maximum value, more or less. So it gets very, very close to, let's say 98, 99% to its maximum value, right? But it takes much longer time to reach its, 100% of its maximum value, okay? But eventually it does reach its maximum or equilibrium value, right? And this graph over here represents, again, di dt. That means changing current as a function of time. You can see, right, again, very rapid change. That means current, or di dt, right? Initially is large, so you have a very rapid change, and then again it's kind of gradually saturates. So that's kind of like what you get. That means, again, di dt is exponential, right, and decreasing, because di dt is just a change in current, eventually, let's say, decreases, right, and becomes zero. That means as soon as the current reaches its maximum value, you can say that it doesn't change anymore. That means no more change in current as a function of time. All right, so the time rate of change of the current is a maximum at t equals 0, okay? And that means, as soon as you close the switch, you have the maximum amount of, change in current, because it goes from 0 to some value, and that happens, to represent the maximum amount of change in current. After that, the self-induced EMF, right, the back EMF slows down the rate at which the current is changing. It is still changing, but at the low, at decreasing, let's say, exponentially decreasing, let's say, the curve, as you can see in the graph. Okay, so it falls off exponentially as t approaches infinity. Okay, and what you get here is this. So this equation represents changing current as a function of time. Okay, again, EMF over L. This represents basically maximum change in current, right? So basically this will be, so di dt equals EMF over L. And this comes from this EMF of the inductor equation. Remember, it's L times di dt, right? So then you can see, right, if you divide both sides by L, then you get EMF over L is equals to di dt. Okay, and let's say when this is maximum, it's equals to exactly that value. Okay, but after that, it decreases exponentially as negative t over tau. Okay, again, tau representing, L over R, which is the time constant. How long does it take for it to decrease by 63% roughly? All right, so let's say we let the current reach its maximum value. Okay, that means we have now maybe some time has passed, maybe like few seconds, few minutes even, right? Let's say usually we say, okay, so let's say it reaches maximum in 5-10 minutes. Okay, that means we wait until it's completely becomes like, let's say, uniform and steady. That means the current in the circuit is pretty much at its maximum. Okay, so that means what we have here is this. Now I have a maximum current. Okay, so if I'm looking at that equation, right, EMF minus I times R minus L times di dt equals 0. Well, think like this. If I is maximum, that means di dt is 0. That means this guy here is 0. That means at this time, right, at this time when current here reached the maximum value, inductor is just like another wire. That means it's just part of the wire. That means even go like this, right? But it's a wire. That means it doesn't affect your circuit in any way. It becomes just wire. That means all you have here is EMF minus IR equals 0. You can see, right, I maximum is equals to EMF over R, just like we talked about. Because when, at some time t, when the current is maximum, inductor is no longer acts like a circuit element. That means it doesn't, change the potential in the circuit. And you can see, right, all the potential difference, all the voltage provided by the battery goes directly, to your resistor. Everything is basically across the resistor. That means all the energy is dissipated by the resistor. Okay. All right. So, and it's for now, right? Like let's say it's fine. So we start with that. Okay. So that means we close the switch S1, right? And then we waited until the current is maximum. Okay. And now the current is maximum, right? Then in terms of the application, right? So let's say at this point, you know, as an application, right, inductor doesn't do anything. So it just sits there and, you know, basically just generates some heat maybe, but other than that, it doesn't do anything. Okay. But here's then what else we can do. I can take the switch S2 and throw the S2 from A to B. All right, so what happens when I do that? Well, what happens here, as soon as I do that, you can see, right, the battery is no longer part of my circuit. So my circuit here is this guy here. And then the EMF is no longer just a wire. So what happens here is this. As soon as I throw the switch, remember that was, you know, at T equals 0, you can say that I still had the maximum current in, you know, through the resistor, right? Going like this. But as soon as I switch it to B, then what I get here is I get this circuit over there. Well, the battery has been eliminated. Okay, and I have only a resistor and an inductor. Okay, so you can see, right, then what I get here is EMF over the resistor plus EMF over the inductor equals 0. Okay, which means that what we're getting here is potential. This is the loop rule, right? So this was that loop rule. It tells me that potential, right? Or you can say that potential that was across the resistor when I close the switch, you know, from A to B. Now that plus EMF across the, you know, inductor, that equals to 0. That means what we get here is this. As soon as, can I go back over there, right? As soon as we do that, right, then the current here will start be dissipating by the resistor. You know, let's say if I didn't have this inductor, it was just a wire, the current right away will be dissipated by the resistor. Okay. But now I have an inductor there, which means that as soon as you start dissipating the current, right, and this current starts going to, you know, decrease because it's no longer connected to the battery. That means all the charges that I have, all that energy that I had right now when I throw the S2 to B, going to start dissipating through the resistor. In that case, then inductor starts to oppose now this change. Now what you have here, you have the current starting from its maximum starts decreasing, right? But it doesn't just go down to its 0 because now EMF opposes that change. It doesn't like the current to go down to 0, so it's going to try to, you know, let's say fight back. And what it does here is instead of current going instantly to 0, it decreases the current you know, like let's say gradually like this. Okay, it decreases it gradually. Okay, so that's kind of what we get from here. So this is the maximum current at T equals 0. Remember, this is when the S2 goes to, you know, goes to point B, right? So that means at T equals 0, we have a maximum current, but then instead of the current going down to 0 instantaneously, right? The inductor tries to oppose it and is more or less successful in, you know, decreasing the current gradually to 0. It doesn't go to 0 instantly, it goes to 0 gradually. Okay, that's kind of what we get. Now, in a let's say previous case, when you when the switch S2 was at point A, right, the inductor was trying to oppose the increasing current. Here is going to try to oppose decreasing current. Okay, and we get the solution as the current doesn't go to directly to 0 instantly, but it decreases exponentially until it gets to 0. Okay, so that means this is initial current, or, you know, maximum current, and maximum current times e to the negative t over tau. Again, tau is that, you know, the time constant, right? That means the current is decreasing with time. And this is very useful because, let's say, a lot of times when you have a circuit and let's say the current goes, let's say, from 0 to maximum or from maximum to 0, like very quickly, it can actually burn some of the, diffusers and things like that in your circuit. So what we can do here, we can put a, inductor in the circuit, and as soon as, let's say, the switch is closed, instead of the current to go to maximum, instantly, it takes a little time. So that means your circuit is, has a chance to, get ready for the, current in the circuit. There's all this, moving charges, right? So let's say, when you have a circuit that is operating, and for example, it's operating at the maximum current, right? And then, for example, you turn the switch off or something like that, and instead of the current to go from maximum to 0 instantly, which can sometimes again damage your circuitry, inductor prevents that instant, decrease of the current from maximum to 0. It makes it gradually decrease, and it allows it time for your circuitry to, let's say, prepare and, let's say, shut down properly. So that's why these are the very important devices that, act like a buffer, right? So nothing goes from, 0 to maximum or maximum to 0 instantly, but, it does that as a function of time and allows for the circuit to basically properly turn on or, let's say, shut off. All right, so let's look at an example here. So we're considering the circuit with the EMF as 6 volts, inductor as 8 millihenry, and the resistance as 4 ohms. So this is like an RL circuit. Okay. What is the inductive time constant of the circuit? Okay, that means basically we want to find the time constant, tau. Well, this is simple enough, right? L over R. So this is 8 times 10 to the negative 4, so negative 3 Henry, and divided by 4 ohms. That means you basically divide the inductance value over the resistance value, right? So, 8 over 4, so you get 2 times 10 to the negative 3 seconds. That means 2 milliseconds. Okay, that means 2 milliseconds is the time that will require, the current to reach its, 62%, 63% of its maximum value. That means when I close the switch, the current that I get is gonna increase, but in 2 milliseconds, it will reach this time tau, right? Or let's say, sorry. So the current will reach this time tau, which is about 0.63% of its maximum value. All right, that's basically the time constant. Part B says calculate the current in the circuit 250 microseconds after the switch is closed. Okay, that means we want to find what is the current at this particular time. Okay. All right, so that means we're assuming that at this, during this time, the current is increasing. That means I can use this equation. So this was part A, this was part B. So the current as a function of time is equals to its maximum value, then times 1 minus e to the negative t over tau. Remember, the maximum current here is EMF over the resistance value, right? And then 1 minus e to the negative t over tau. That means what I get here is 6 volts over 4 ohms. That's the EMF over R. Then 1 minus e to the negative, and then here I get 250 microsecond. I can write it as 0.25 millisecond. This is the t. Then divide by the tau, and the tau, remember, was 2 millisecond, because then I can cancel the units, right? Millisecond over millisecond, and then, calculate that. And what I will get here is this, 0.176 amps. It means roughly 176 milliamps. That will be my current, 250 microsecond after I, we close the switch. Part C says, what is the value of the final steady state current? All right. So for that, I can use, equation EMF from the battery divided by the resistance. Remember, this is how you calculate maximum current. So 6 volts over 4 ohms should give me 1.5 amps. That means the maximum current I'm going to have here is 1.5 amps in the circuit. All right, so part D says, after what time interval does the current reach 80% of its maximum value. All right, so now I know that the current is going to be 0.176 when you have 250 microsecond, and in 2 milliseconds it's going to reach about 63% of its value, and 100% is 0.15 amps. But let's say how long it will take for it to reach 80% of its value. Again, still we're considering the time when the current is increasing. So I'm using this equation. Current is equals to, so maximum current, then times 1 minus e to the negative t over tau. Remember, my goal here is to find that particular time over there, right? But remember, what I'm given here is, I'm given when this guy here, right, this guy is equal to the 80% of its maximum value. That means I can rewrite this in terms of 0.8 times I max. Okay, 0.8 times I max, which means that on the left side, I have 0.8 times I max. On the right side, I have I max. That means I can just cancel those two. Okay, and what we get here is I get 0.8, because that was the 80%, right? So 0.8 equals then 1 minus e to the negative t over tau. All right, so, and I rearrange, I say, okay, so e to the negative t over tau is equals to 1 minus 0.8, or just equals to 0.2. Okay, and then to get the t over there, I need to then take ln of both sides. Okay, where if I take ln of the left side, which is ln times e to the negative t over tau, I get negative t over tau. On the right side, I get ln of 2. Or sorry, ln of 0.2. Okay, and all I have to do, you can see from here, right? Then t is equals to negative tau times ln of 0.2. Okay. Well, if I do this calculation, plug in the value for the tau and times ln of 0.2, we will get 3.22 milliseconds. Right? That means it's going to take 3.22 milliseconds for the current to reach its maximum value. All right. And in a way, you can use the same equation, right? So basically, to always find current at any other time, 20% of the maximum, 30% of the maximum, 50%, 100% of the maximum, right? You can always use this equation, right, to find the time for that particular, current. All right. Here's then one other modification we can do to our circuit. Let's say we put switch 3. Okay. So with switch 2 set to position A, okay, and the switch S3 closed, we get current in the conductor. Okay. Now, what do we achieve with this? Okay. So remember, if I have the switch S2, so this is basically a closed circuit. Switch S1 is closed. It's a closed circuit. So I'm going to get a current. Okay. So technically, the idea is that there's going to be current, moving toward this, toward the resistor. Okay. But what I get here is this. Okay. You can see that the current, when it reaches, let's say, this particular point, let's say junction point, right? It has 2 paths to go. One through the resistor, the other one above the, the path through the switch S3, right? And obviously what we're gonna get here is the switch, switch S3 is, a preferred path for the current. Remember, we're assuming those are ideal wires and there's basically no resistance there at all, okay? That means the current basically gonna bypass the resistor and just gonna go like this, okay? Just gonna go like that. So what we get here is, in a circuit with an inductor, the battery must supply more energy than in a circuit without an inductor. Because one of the things we get here is, well, we get no resistor in the circuit anymore, okay? And that means you have just a EMF and the, let's say inductor itself. There's nothing else there, because that switch S3, when it's closed, it assumes that the current always going to go through that path and completely ignore the resistance. Okay, that means you have just the inductor. And what we get here is the battery has to now supply more energy than, let's say, if there was no inductor. Okay, and the reason is, more or less probably should be obvious, because remember, when you have just a resistor in the circuit, and let's say you turn on the battery, right? The resistor, doesn't fight the increasing current, where the inductor fights the increasing current. That means the EMF not only going to try to, generate that, current, it's also going to try to generate and more to fight whatever the, let's say, generated induced current by the inductor. Okay, because part of the energy supplied by the battery appears as internal energy in the resistor, and then the remaining energy is stored in the magnetic field of the inductor. Okay, and what we get here is inductor. Remember, inductor has a magnetic field, right? If there's an induced EMF, it induces its own magnetic field, and there's energy stored in those magnetic field lines. Okay, because the inductor has a very similar role in the circuit as capacitors. It can act like a storage of energy. Okay, so technically then, resistor dissipates that energy into become like a internal energy, which you can't take it back. But when the energy is stored in an inductor, the energy is stored in magnetic fields, and that energy technically is retrievable. You can retrieve that energy. Okay, and we're going to take U to be the energy stored in the inductor at any time. And what we get here is change in energy as a function of time through the, let's say, inductor. Remember, so that let's say that EMF is, remember, like du dt, right? So you can say that the work done, right, as a function of time. So then what you get here is, so let's say, I'll put this here. This is technically a power, right? So the power will be, remember the EMF was L di dt. So remember, if I multiply current and EMF, this is power. That means I take this guy and multiply by current as well. So again, that L times I times di dt. This is basically the power, right? Which is the, the rate that, energy is stored or dissipated or used across that inductor. So we get this. So basically du dt equals Li di dt. Okay. And then from here, we can kind of see, right? So let's say dt can cancel out. And then here, I just basically integrate both sides. And what you end up here is, you can see, right? Li is a constant. So here on the left side, right, the integral of du becomes just u. And then on the right side, since we cancel the dt's, I have then L times I times di. That means I'm integrating from 0 to its maximum I. Okay, and if I, Li is a constant, can come out, so then you have from 0 to I, sorry, L is a constant, so then I di, and that gives me 1/2 I squared, so then 1/2 L times I squared. That's the energy of the inductor, the amount of energy stored in the inductor, right? That basically is stored in the magnetic fields of the inductor. And it's very, very similar, right, to the capacitor, which the energy was 1/2 QC square. So Q square times C, so basically. Okay. So what we do here is this then. Now switch S2 is thrown to position B, which means we eliminate the battery. Then the current persists in this ideally resistance-free and battery-free circuit consisting of only the inductor and the conducting path between its ends. That means, again, so what happens here is this guy here is, invisible to the circuit because there you have the more preferred path. And then you get just this, where you have just the inductor and, ideal wires, right? So there is no current in the resistor, so no energy is being delivered to that. Okay, and what can happen here is the inductor can hold on to all those stored energy. It can hold on to that all the stored energy, just like the capacitor can be, storing energy and then holding on to that. If you basically charge the capacitor and keep it, outside of, like, let's say, circuit. Same idea is here. Okay. That means, what you get here is, let's say, as long as the switch 3 is closed, then you get a circuit where there's only inductor holding on to all of that energy. Okay. But then what we can do is this. Switch 3 S3 is basically open. Well, if you open S3, but S2 is still at point B, then your circuit becomes this. That means what we have here is there is a resistor that can try to start dissipating the energy stored in the inductor. And that's basically what you're going to get. So there's now a current in the resistor and energy delivered to the resistor. That means you can then think of like this inductor acts like a temporary battery because it has an EMF across. Because now the resistor starts dissipating energy, and inductor going to try to fight that. Okay, so where is the energy coming from? So the only other element in the circuit is the inductor, right? That means energy therefore is stored in the inductor and is now being delivered to the resistor. So think like this. So if there was a light bulb over there, the light bulb will be basically bright depending on how much current you have, right? But it will be operating. So the light bulb will be operating even though there is no battery connected, right? It's connected to the inductor, but inductor has some kind of stored energy, so it's using that energy. Just like if you can connect that light bulb to to the capacitor, it will try to then draw the energy from the capacitor. Okay, that means inductor, just like a capacitor, can act like a temporary battery. Okay, and remember that energy here was 1/2 Li squared, right? So we can even calculate amount of energy was there. And sometimes we can also calculate energy density, which is energy per volume, right? Energy per volume. So you can kind of rearrange that, and what we get here is we get this equation once you, let's say, take the energy divided by A times L and replace the L with N times flux over the current, which is N times magnetic field times area over the current, right? So you do all of those things, and what you're going to get here is you're going to get basically a constant like that. Okay. All right. So let's look at our last example here. And this one is basically considering another RL circuit, right? The same circuit where switch S2 at position A and the current having reached its steady state value. When S2 is thrown to position B, the current in the right-hand loop decays exponentially with time according to the expression I equals, so the maximum current, or I is a function of time, equals, so this is maximum current, then e to the 2 time over tau. Okay, so that's what we're given in terms of, like, let's say our current as a function of time expression, where the initial current or the maximum current equals EMF over R. So initial current in the circuit and the T equals L over R is the time constant. Okay, so what we're going to be asked here is to find that energy stored in the magnetic field of the inductor appears as internal energy in the resistor as the current decays to zero. That means how much energy we have stored, right? It basically becomes same amount of energy that will be then dissipated or decayed by the resistor. All right, so remember that means du dt is the energy dissipated by the resistor, generally written as I squared times R. Okay, remember this is basically looking at the rate at which the energy dissipated by the resistor. It's I squared times R. Okay, now we're given that I here is the I max, right, and e to the negative t over tau. Let's put it like that, right? And then times R. Okay. And what we get from here is, if I do that, right? So remember, there's also a square. So if we do this, we're going to get then I square e to the negative 2. And remember, tau here, L times R. So I can just represent this as RT over L. Okay. So basically, and then times the resistance value. Okay. So this is my du dt. Okay. Then what I get here is I integrate both both sides. Left side's integral of du dt from 0 to u, we end up with u. Okay. On the other side, I have then, I square e to the negative 2 r t over tau times r. And this is basically what I'm going to be doing here is, so moving this t to the other side, right? First, before doing the integration. So I get this. So I'm going to be integrating with respect to time from 0 to how long it takes. And generally, we can say that infinitely amount of time takes until it reaches its maximum. Okay. And here, I initial square time resistance, those are the values that constant, doesn't change. And I do that from 0 to infinity. I basically have negative e to rt over tau dt. So those are the things that I'm going to be integrating, right? Once I integrate and once I evaluate, what we're going to get here is current I square times r, that, what I had already, constant comes out. And then integral basically give me L over 2R. Okay. And then R is going to cancel out. And what we can see here is we get 1/2 Li square. Remember, we were calculating the energy across the resistor, and we can see that it's equals to 1/2 Li square, which was exactly equals to energy of the inductor. Okay. That means we can show that energy dissipated by the resistor is equal to the energy, that was available, across the inductor. Okay. All right, so that's it for this chapter. So we're going to conclude this. Make sure you guys finish the homework problems. Next week, we're going to start chapter 24.